Hello, I'm Random Tensor and welcome to my channel. Since this is the first video on my channel, I'm going to give a brief introduction about myself and the idea behind this channel. I have a PhD in electrical engineering with a focus on statistical signal processing, along with a handful of other degrees all related to electrical engineering or mathematics. The idea behind this channel is to provide short but mathematically rigorous expositions on topics ranging from pure math to artificial intelligence. So this will include things like statistics, signal processing, and machine learning. Today we are going to go over Markov's inequality. And like many earlier results in probability theory, Markov's inequality was either discovered by a Frenchman or a Russian. A good rule of thumb to determine which is to ask yourself the question, would this result aid me in the running of a casino? And if it wouldn't, then it is probably discovered by a Russian. Markov's inequality was not actually discovered by Markov. It appears in some earlier sources, including some works by Chebyshev, who is Markov's doctoral advisor, but don't worry, Chebyshev is going to get his own pretty cool inequality. So yeah, let's get started. Okay, so for Markov's inequality, we are going to be looking at a random variable x on the real number line. And we are going to assume that, well, we could assume that x is distributed according to an arbitrary probability measure. However, we will assume that x is distributed according to a probability density function for simplicity. But if you're familiar with rigorous probability theory, adapting this proof to general measures should be no problem. And what we want to show is something akin to the following. If the expected value of x is small, then the probability that x is large should also be small. And so this makes sense if you think about it for just a moment. If x is small on average, then we should hope that the probability that x is large, well, it shouldn't be big, frankly. To write this, we can change this statement to be more mathematical by the following. Expected value of x less than or equal to a should imply that the probability that x is greater than some alpha should be less than or equal to some beta. And to get started on this, we should consider, is this statement here on the left enough to get us to the statement on the right? And the answer is no. And we can show this by a fairly simple counterexample. So if we have that the probability density function looks like the following, where we have a large spike at negative 100 and another large spike at 100, then it follows that the expected value of x is equal to 0 because these two spikes balance each other out. But we also have that the probability that x is greater than, let's say, 99 is equal to 1/2, which is large as far as we're concerned. And we could basically make this as pathological as we want it to be. We can take these spikes, and send them off arbitrarily far, and still have an expected value of 0 and still have a probability that x is basically as large as we want it to be. So we need to add a little something to make this possible, and what we are going to add is we are going to assume that x is greater than or equal to 0. And this is enough to get us to a very basic statement of the form that we would like to get to. And the basic trick we're going to use is the following. We can change a statement about probability. So we have x lying in some set A. We can change this into a statement about expectation by simply looking at the expectation of the indicator function of the set A of our random variable x. What is the indicator function? The indicator function of some set A assigns of x, don't forget that. It assigns a value of 1 when x is in A, and it assigns a value of 0 when x is not in A. So just to look at a visual example of this, if we have that our set A is denoted by these little squiggles that I'm making, then the indicator function looks like the following, where this has a height of 1. And this is pretty easy to see, and I'll do it. Why this is true, I'll show by sort of beginning the first step of our proof. So what we are interested in is the expected value of the indicator function of the set that is greater than alpha. Y is greater than or equal to alpha of x. And using the definition of expected value, we have that this is equal to the integral of the PDF of x times the indicator function of the set that is greater than alpha dx. And this is just equal to the integral from alpha to infinity of p of x dx, because everywhere outside of this set that we're integrating over is 0 because of our indicator function. And then this is just equal to the probability that x is greater than or equal to alpha. So what we've got is that the expected value of the set greater than or equal to alpha is equal to the probability that x is greater than or equal to alpha. And so we've got the part of our inequality that we want written down here. So we need to figure out some way to get control of this. And the way we're going to do this is via a simple observation. If we have the expected value of some functions, let's say f of x, and the expected value of g of x, if f is always greater than g, then we have that the expected value of f is always greater than the expected value of g. Quite simple to show this. We simply do the two expected values, dx, and integral of p of x, g of x, dx. Since both of these multiplans are positive, we know that this term on the top will always be greater than or equal to this term on the bottom. So what we need to do is simply find some function f of x such that it bounds the indicator function y is greater than or equal to alpha nicely. And we can do this by a fairly simple visual argument. we have that the indicator function looks like the following, where this is alpha. And we can bound it by a simple linear function as follows. So we're going to have that f of x, well, it's linear, so it looks like x, and we have a rise of 1 and a run of alpha. So we have x times 1 over alpha, which is equal to, well, it's just x over alpha. So to finish everything up, we have that the expected value of x over alpha is greater than or equal to the expected value of the indicator function of the ray that is bigger than alpha of x. And we know this from the little dominating argument we made before. And we know that this, by linearity, is simply equal to the expected value of x divided by alpha. And we know that this is equal to the probability that x is greater than or equal to alpha. And we're done. So we have this nice way of bounding the probability that x is greater than or equal to alpha when we know the expected value of x, so long as x is greater than or equal to 0. Now this is a pretty rudimentary way to bound the probability of x, but it kind of serves as a starting point for controlling where x can be given things like averages and variances, tail properties of random variables, and so forth. So it's a nice starting point for this kind of thing. So anywho, I would like to say thanks for watching. I realize that this negative first video doesn't have the most amazing presentation and so forth. I'm quite new to this, figuring out all the tools on my own, but I'm hoping that by episode 1, I'll have things looking a little better. And yep, thank you for watching.